All right, maybe we could start. So hi everyone. Today we are very happy to have David Kolchemeyer. Am I pronouncing your name correctly?
Yeah, Kolchemeyer.
Kolchemeyer. Give us a talk from Harvard. Give us a talk about the eigenstate thermalization in Jt Gravity with matter. Thanks so much. Please.
All right. Yeah, thanks. Thanks very much for having me here. Yeah, so I'm happy to talk about the ETH and JT gravity with matter. And this is particularly exciting for me because this is not based on a paper that has already appeared, but it's based on current work in progress with Daniel Jafferis, Baur Mukhametzhanov, and Julian Sonner. And so if you have any questions or comments, please, or suggestions, please feel free to let me know. But basically, I'll explain some results we have and some results that we hope to get soon. Okay. So let me start with the introduction. So the Eigenstate Thermalization Hypothesis is an ansatz for matrix elements of simple operators in a chaotic quantum many-body system that explains how the system can effectively thermalize without coupling to a bath. So here's the basic ansatz. So here I and J refer to energy eigenstates, and we're considering these matrix elements of a simple operator O. And there are two terms. One of them is proportional to the identity operator. It only depends on the energy and no additional information about which eigenstate we might be considering. And then the other term here is suppressed by the microcanonical entropy, where S here is microcanonical entropy of some microcanonical window of a specified energy. And I guess the thing that we'll be most interested in this talk are these coefficients here, Rij. So these coefficients are, well, they behave as if they're drawn from some random statistical ensemble. So they have erratic oscillations, but one should still be able to talk about the statistical properties of these coefficients. And I guess the good thing about this ansatz, or what it succeeds in doing, is that it implies that late time observables computed in a single energy eigenstate are in fact well approximated by the microcanonical ensemble. So, the initial state could be some arbitrary superposition of different eigenstates in some small microcanonical window, and then at late times, observables involving this O will essentially just depend on the microcanonical ensemble itself, and not the details of which eigenstates you chose to make the initial state.
Actually, quick question, David.
Sure, yeah.
So when you say late time here, do you mean polynomial time and energy? Do you mean, what is late time here?
Yeah, that's a good question. Well, basically, I'm just referring to, so I'm just referring to, I guess, something that you do mathematically, where, for example, you could have, a sum over eigenvalues, something like this. And the idea is that if you could take some like late time average, then a sum over two energies like this effectively collapses into a sum over single energies. Yeah, so I'm just referring to this kind of replacement that one might make. Right, so let me see. Well, I guess the time has to be sufficiently late to compare. Yeah, so I guess the time scale that we should consider should be roughly, I guess, guided by the energy level spacing of the eigenstates.
So I think if your system is non-chaotic, like free field theory,
right.
after a very, very long time, it will still be ergodic, right? Even if you don't have ETH, well, not ergodic necessarily. Well, right. Maybe we could discuss this offline, but my guess is that you probably need polynomial time and energy suffices. You don't need to have e to the power of s.
I see. Okay.
Nima, isn't this just thermalization time? That's why it's called eigenstate thermalization, no?
I think so too. So, so thermalization would mean that time order entropy, right? Like polynomial in entropy.
I see. Okay. Yeah, that makes sense.
Because
right. Yeah, this is
not
just thermalization
ergodicity.
time.
Yeah.
Okay.
Thank you.
Yeah, thank you. Great. Okay. Good. So we have this ansatz here. And basically, the question that I want to kind of raise in this talk is how good of an approximation is this ansatz in a given chaotic theory? So I guess the point is that this ansatz doesn't make an explicit reference to time, but I guess it's expected to be a better approximation to some chaotic theory after the thermalization time. But one still might want to ask, how good of a representation of the matrix elements in some given theory is this ansatz across different timescales? And another point I wanted to raise related to this is that we could be considering some theory, like maybe some theory in 1 + 1 or higher dimensions, where the simple operators come with positions and they have to commute at space-like separation. And so in general, if we draw the matrix elements from some random ensemble, they would fail to commute at space-like separation. So in general, we might expect that for more complicated theories, like theories with locality, there are some constraints that have to be obeyed, and maybe some refinement of the ETH might be necessary. Or that maybe this ansatz as written here shouldn't be applied at face value. So that's an idea I want to explore in this talk. Right, so in particular, I want to look at this question in theories with the semi-classical gravity dual. So the question there is, in that case, what does the gravitational path integral say about the distribution of these random matrix elements? So recent work over the past few years, such as by Saad Schenker-Stanford and Kotler-Jensen, suggests that the statistics of energy eigenstates is encoded in non-perturbative wormhole contributions to the gravitational path integral. So what we've learned is that the gravitational path integral knows not only about the density of states, but also about higher moments of the density of states, or the statistics of energy eigenstates. And so the purpose of this work is to try to go a step further and to make statements about the statistics of the matrix elements of simple operators using the gravitational path integral. So we want to see if we can clarify the relationship between the gravitational path integral and the ETH, or some refinement of it. Right, and so as mentioned in the title, we're going to make progress in this direction using a toy model of Jt gravity coupled to a free massive scalar. And the boundary operator dual to the scalar field, I'm going to call it O. Good. And so here we're going to use a matrix model to describe the matrix elements of O, and we're going to compare the results to the gravitational path integral. So let me just give a brief outline of what is planned for the rest of the talk. So first, I'll just review Jt gravity with matter and how we compute correlators. And then I'm going to write down a Gaussian matrix model, and I'm going to relate it to some wormhole phenomena in the bulk, and I'll explain where the Gaussian matrix model succeeds and where it fails. Then I will show that the gravitational path integral itself actually implies that in the putative dual matrix ensemble, the matrix elements of the operator O should obey a non-trivial constraint. So I'll explain what that is. And then after that, I'll introduce something that I like to call q-deform Jt gravity. Also, it's related to the SYK model, some double scale limit of the SYK model that you might be familiar with. And this is just an analog of Jt gravity that does not obey the aforementioned constraint. And basically for this reason, I'll explain why q-deform Jt gravity is more likely to have a conventional matrix model dual. And then after that, I'll explain how this constraint will lead us to a conjecture about the form of the matrix model potential, and how we intend to test this conjecture using q-deform Jt gravity. And also, if time permits, I can comment on some more technical aspects of this work. In particular, there's some interesting connection between these SL2R 6J symbols that appear that I'll explain later, and one-dimensional conformal blocks that could be of a technical tool in solving some equation I'll discuss later, if time permits. Okay, so now let me just quickly review Jt gravity with matter. So the Euclidean action of Jt gravity basically has three terms. So first is the topological term, and all this does is just means that you get some factor of e to some power times s naught associated with the topology of any diagram that you write down, where s naught is interpreted as the extremal entropy, and e to the s naught basically governs the spacing of energy eigenvalues. then the next piece is the Jt gravity action. So here, it just, we know that the dilaton acts as a Lagrange multiplier, and so Jt gravity is a theory of constant negative curvature manifolds. And then finally, we have the action for a scalar field, a massive scalar field of mass m that's propagating on this background, and it only interacts with the Jt gravity fields through the metric, and it doesn't interact with the dilaton directly.
Can I ask a very basic question?
Sure.
So in the first line of the action, you have chi. Is this something like you choose?
Oh, sorry, thanks. Sorry, chi is the Euler characteristic. Sorry,
Okay.
I should have specified that. Thank you.
Thank you.
Good, thanks. Right. So, okay, now just a word on boundary conditions. So on an asymptotically ADS boundary, basically we can fix the boundary length and the value of the dilaton. So we take Dirichlet boundary conditions and we take both of their values to infinity while fixing their ratio. And this determines beta, which is the inverse temperature associated with that asymptotically ADS boundary. And as for the massive scalar field, we have a choice of boundary conditions that determines the scaling dimension of the boundary operator, which is given here. We should make sure to choose the plus or minus sign to keep delta greater than 0 to get something sensible on the boundary. Okay, so in this talk, we're mostly going to be interested in disk correlation functions with an arbitrary number of insertions of the operator O on the boundary. So without Jt gravity, if we just turn gravity off, then if we take the correlators of the bulk scalar and just extrapolate them to the boundary, they become correlators of a generalized free field, GFF, and then we can just compute them by Wick contraction in a pretty straightforward way. So now if we want to include the gravitational dynamics, all we need to do is start with a GFF correlator that we computed with Wick contractions, apply a reparameterization to it, and then integrate over all the reparameterizations with this Schwarzian action, which can be derived from the action I showed on the previous slide. But I'm not going to explicitly give its expression here because I won't explicitly need it. But the point is that the gravitational correlators are very closely related to the non-gravitational correlators just by integrating over reparameterizations of the latter. And what's interesting, or what's nice, is that these infinite dimensional integrals can actually be computed exactly, or more precisely, they can be reduced down to finite dimensional integrals using a certain set of Feynman rules that have been developed in these papers here.
Sorry, a quick question. So you want to integrate over the whole diffeomorphism group of the circle? You are not modding out by anything?
Oh, no, sorry. We want to mod out. Sorry, I should have been more clear. Yes, we want to mod out by SL2R.
Okay.
That's a gauge symmetry of this action. Yeah, thank you. I should have specified that. Okay. So good. So now let me just briefly review these Feynman rules here. Yeah, so each Feynman diagram here represents a Wick contraction of the operators in the GFF theory. So here's the ADS boundary, and here I have 6 operators, and I just chose a particular Wick contraction. So, what we need to do is we need to label every region in this diagram by a parameter S, which I've taken to go from S1 to S5. And for every such region, we have an integral over the density of states, the disk density of states of the theory, which is shown here. And furthermore, for every boundary segment, which is labeled by the length beta, we include e to the minus beta s squared. Now, the rest of the integrand of this integral is given by the following rules. So basically, wherever you have this bulk blue line intersecting the ADS line, you get the square root of a product of 4 gamma functions here. So I might use this shorthand notation sometimes just to specify a product of the 4 gamma functions with parameters S1 and S2 and delta. And then perhaps more interestingly, when you have an intersection of these 2 matter lines in the bulk, you get this special function here called a Wilson function. and it has an interpretation of being a 6J symbol of the SL2R algebra. And I'm not going to give the explicit definition of the special function here because it looks a little complicated and won't be immediately useful for this talk. But what I'll just say right now is that the symmetries, so this is a real number, and the symmetries of this special function are basically the symmetries of this Feynman vertex over here. So this includes reflections across these two lines and cyclic translations.
Oh, sorry, David. Can you say a few words about what is the physics of the label SI?
Oh yeah, definitely. So the label SI, I guess it should have the interpretation of entropy above extremality. So if you just study like classical or semi-classical Jt gravity, the energy goes as the square of the value of the dilaton above the extremal value, or equivalently the value of the entropy of a black hole above extremality. So I think the reason why the letter S is used is because like S is entropy.
And then, sorry, what does it mean to say now you have a function rho of SI? So it's the density of an entropy?
Oh, okay. So this entropy interpretation, I guess, is really only precise in the semi-classical limit. So when you take the semi-classical limit in Jt gravity, the way to do that, like given any expression that you've computed here exactly, if you want to take the semi-classical limit, you consider the limit that S goes to infinity. So the semi-classical limit is like a large S limit. And so in that case, so this rho is like a sinh 2 pi s. And so at large S, this looks like e to the 2 pi s. And then that's, you know, that's the correct expression for like summing over states. You exponentiate the entropy, right, with a factor of 2 pi.
Is it some sort, does it have some sort of interpretation in terms of the density of states of a particular representation, or
the density of states of a particular representation?
I mean, I'm struggling to understand. You're associating SI to regions of that diagram, and I'm not quite seeing what's the physics of it, because you have rho of S, which is like a density of states, right?
Yes.
So which is, I imagine, it's a counting of energy eigenstates.
Yes.
So S, I guess, would be an energy label.
Yes. Yeah. Oh, yeah. Okay, good. Right.
But then what does it mean to associate an energy label to a region?
Right. So in matrix models, we do this. So I'm going to write down a matrix model where the eigenvalues of the matrix correspond to energy eigenlevels. And then in planar, you know, Feynman diagrams for matrix models, whenever there's a loop, we sum over all the, like we do a sum over the energy eigenvalues. Like a loop corresponds to a sum. And
okay, maybe, yeah, we'll explain this later.
Yeah, so I'm going to argue soon that these Feynman rules have, like, they immediately kind of lend themselves to a matrix model interpretation that I think is extremely natural. And then the real test is to find quantitative like checks between these gravity Feynman rules and a matrix model. And that's the point of this work. Okay, thank you. Yeah, it's a great question. Okay, so moving on. Okay, so I should just mention here some interesting identities that these 6J symbols obey that I'm going to use later. So the first one is this Yang-Baxter relation here, which just says that if I have 3 matter lines that cross, I can move this line over to the other side. And this is just necessary for the consistency of the Feynman rules, so that, you know, there are different ways that these Wick contraction lines can move over each other in the bulk, and they all have to give the same answer. Then there's another relation, which is not necessary for consistency, but which is interesting, which is this orthogonality relation. So mathematically, it can follow from the interpretation of these functions as 6J symbols. But right now, I'll just associate this identity with this picture over here, which is that if I put 2 of these cross lines together and then integrate over the region in between, it has the effect of uncrossing these 2 lines. And so when I have these 2 S labels in the same region, then that should be interpreted as a delta function, because those 2 energies need to be the same. So I will revisit this later. Okay, Good. So now with that out of the way, I'm going to talk about the Gaussian matrix model. Okay, so let's consider a two-matrix model with Hermitian matrices H and O and a single trace matrix potential. And so the point is that the matrix potential we're going to consider has a complicated dependence on H, but it's a simple function of O. So here's the matrix integral. And here I wrote the single trace matrix potential in the eigenbasis of H, which I'm interpreting as a Hamiltonian. And so E are the energies here. So first, VSSS refers to the matrix potential that Saj, Shanker, and Stanford used in their single matrix model. And then here I have a term. So OAB are just the matrix elements of the operator O, and F is just a smooth function. And so the point is, if I do a series expansion in F, like a power series, I get powers of EA, powers of EB, where these are the energy eigenvalues of the matrix H. And every such term in the series expansion corresponds to a trace with two O operators and then some number of H's. And so the point is that in this term, we can capture all such contributions. And here I've introduced a single trace counterterm potential. The purpose of this is that so when I integrate out the matrix O, I can generate a potential for H, and that could potentially shift the disk density of states away from the one that's associated to the disk in Jt gravity. And so this counterterm potential just corrects for that. Okay.
Sorry, can you say it again? What's the role of the counterterm? That was a little bit quick for me.
Yeah, I'm gonna come back to that later, actually.
Okay, sure.
Okay, yeah, thanks. I will also write down an explicit expression later, then I'll come back to it, yeah.
Sure.
Okay, so basically this matrix model was designed to produce the correct answer for the disk density of states, as I will come back to shortly. Now we can consider the 2-point function. So to calculate the 2-point function, all we need to do is do the Gaussian matrix integral for O with the insertion of these two O's. And so that gives us the propagator, which was 1 over F. And then that gets inserted into the matrix model for H. And so at the end of the day, there are two sums over eigenvalues that are at play. And so we have two density of states being inserted into the matrix integral for H. And the idea is that to leading order, if we just focus at leading order, then this just becomes the product of the two disk density of states. Okay, so now we have this model's prediction for the 2-point function here. I just replaced this with the two density of states. Okay, so meanwhile, here's the answer from the gravitational Feynman rules. And so we can compare these two answers, and this tells us how to choose the function f. And so once we've done this, now we've fixed all the parameters in our model. And now we can see what our model predicts. Okay, so here, this is just a quick visual illustration of the previous slide. So on the left-hand side, this is just the gravitational diagram that computes the 2-point function. And here, this is the computation you do in the matrix model, where this blue double line just represents the propagator of O. And then when we take the trace, basically we're doing a sum over eigenvalues, and that's what's represented by each of these two loops. And the idea is that the sum over eigenvalues, in the planar approximation becomes an integral over the disk density of states. And that's what is equivalent to the integral over the disk density of states in this region over here. So this is kind of, I guess, going back to an earlier question, this is kind of how we want to associate the gravity Feynman rule logic with the matrix models, that essentially we can almost essentially have a correspondence between diagrams in the matrix model and gravity Feynman diagrams. That's what I'm trying to go for here. And I'll come back to this point later when we introduce interactions. Okay, so now let's consider what happens when we integrate out the matrix O in the matrix model. So when we do this, we generate a double trace addition to the potential for H, which I'll call delta V. So now we have the matrix model for H with potential V plus delta V. And it just depends on the function f, which I fixed earlier, and it ends up taking this form. So now to go from this first line to the second line, well, this first line equals this second line mathematically, except for the fact that this integral is divergent. But the key is that the divergence of this integral can be shown to not depend on the energies. And so it's just a constant that just drops out of the potential and we can forget about it. So this is just another expression then of what you get, the change to the potential when you integrate out the O matrix. Okay, so now I'll explain the role of Vct. So first I'll define what it is. So here's delta V, and I'll define V counter term to be the thing that you add to that such that their sum is this expression here. And so literally all I've done to get here from this line is to take this sum. So we have two sums, and I replace them with two integrals over the density of states. And Vct is chosen to subtract off from the density of states the disk density of states. So basically I replace the sum over eigenvalues with an integral where we subtract off from the density of states the disk value. So we're just considering fluctuations about the disk value. And the point is that when you add this now to the original potential for the SSS matrix model, you can see how it changes the saddle point equation, and the original disk density of states is still a solution to the saddle point equation. And so that's what we want. And so that's the role that the counter term plays. Okay. Okay, so now that we have this, let's see something non-trivial that this matrix model predicts. So when we integrate out O, as mentioned, we get exponential to the minus delta V minus Vct. And I want to give this exponential a diagrammatic interpretation here. I want to think of it, I guess, as e to the, let me see, I'll use the blue color, e to a double loop or a double line loop. So schematically, so the reason why I use double line loop is because the delta V minus Vct is a double trace thing. So I have a double loop here. And so the point is that I can then expand this expression and see the corrections that I get. So let's consider a correction to the connected two boundary correlator, which in the SSS matrix model had an interpretation as a double trumpet. So, okay, so here I have my two traces, and then I'll expand out, and I'm just going to consider the linear term in this expansion, which I've replaced over here. So here I just took the expression from the previous slide, but I did not explicitly write in the counter term, but I'll explain the role graphically that that counter term will play very shortly. So if I just ignore the counter term for a second, then, okay, so then I can just plug this in. I'm just keeping the first term in the expansion. And now I'm going to evaluate the SSS matrix integral, and I'm going to consider the case where this trace here and the trace represented by this integral over this density of states come together in a connected component in the SSS matrix model. And likewise, this trace here will connect with this component here, which I've illustrated here. So one trace connects with one of the lines of the double loop, the other trace connects with the other line. And there are two ways this can happen. So you get a factor of two. So the point is that when you do this and you evaluate it, this is what you get. So you get the usual integral over the geodesic length of a double trumpet here, but now you have this extra expression that depends on B. And this expression has the interpretation of a world line instanton that winds around the double trumpet. And there are two ways it can wind. And so this considers the sum over both ways. And so this is a non-trivial result basically because so the formula for a world line instanton that wraps some geodesic and some hyperbolic manifold is known. And the point is that that formula is exactly this over here. So this matrix model basically was able to non-trivially reproduce the effect of an instanton that winds plus or minus 1 times around the double trumpet. So this is a non-trivial and correct prediction of the matrix model. There is one subtlety though, which is that the world line instanton, in gravity should be allowed to wind more than just 1 or minus 1 times. And so that's not captured by this matrix model. So really only the plus or minus 1 case is correct. So in general, actually, you get the wrong answer. But it's interesting that part of the correct answer was reproduced. Now I'll just comment briefly on what the counter term does geometrically. So the idea is that you could consider a situation where you have the double loop like this that gets inserted into the SSS matrix model. And now you could imagine that perhaps one of these boundaries, say the outer one, will be contracted in a connected diagram with some external ADS boundary, and then perhaps the internal blue loop might just not be contracted with anything else, and it just might cap off into a disk. So now this picture that you get looks like a non-trivial correction to the disk density of states, but I argue that the counter term was designed to make this not happen. And indeed, the geometric role of the counter term is just that any contribution where this double blue loop, where one of the blue loops kind of caps off in a disk, or just appears in a connected diagram just by itself in the SSS matrix model, any such contribution is subtracted by the counter term. And so that's why so that's why we shouldn't consider that. Okay, so I think this is still a nice result that this world line instanton was reproduced, but clearly the Gaussian model still is lacking in other respects. So we can make another comparison here, or another test of the Gaussian matrix model, which is to work at trivial order in this expansion here. So we just forget about this extra contribution when we integrate out O, but we can still work to arbitrary order in the genus expansion of the SSS model. And so, so in this case, let's compute the 2-point function, which again is given by this expression, but now I'm not going to work to leading order here. I'm going to look at the full contribution from higher topologies. And so one can compute the answer in the SSS matrix model, and it was actually shown on the gravity side that this agrees with the following. It agrees with the gravitational disk 2-point function, but also summed over higher topologies, and also summed over all geodesics that can go between these 2 points, as long as those geodesics are non-intersecting. Okay, so again, basically the reason why non-intersecting geodesics aren't allowed is because this is a Gaussian matrix model, and so you can have so you have a propagator for O, but you don't have any interaction vertices for O, and so for this reason you can't have any intersecting geodesics. But still, this still some aspects of the bulk computation can be recovered. Okay. And so finally, for one last check of what this Gaussian matrix model succeeds and fails to do, we can look at the 4-point function here. So if we look at a 4-point correlator in the matrix model side, so again, we do the Wick contractions of these 4 O's. And so there are 3 Wick contractions, but only 2 of them contribute at planar order. And those are the ones that are shown here. Meanwhile, here's the contribution from the gravity answer. So the idea is that this diagram on the matrix model side will agree with this diagram on the gravity side, and same for here and here, but this cross diagram is not reproduced. So in this sense, it doesn't get the right answer. But if we look at certain observables at sufficiently late time, this diagram actually doesn't contribute. So for example, we could look at, so if we inserted this operator at Lorentzian time 0 and inserted this at Lorentzian time t, say 0t, for example, then this would be a contribution to an OTOC, which will decay, after some number of, roughly the scrambling time or some order 1 number of scrambling times. So this will decay to 0. And so then in this regime, this diagram here actually doesn't contribute, and the Gaussian matrix model gets the right answer for the 4-point function. So roughly at early times, the Gaussian matrix model fails, but at late times it succeeds. Okay, so the Gaussian matrix model gets some things right, but gets many things wrong. And so now in the second half of this talk, I'm going to think about what we can say about non-Gaussian matrix models and whether any of these issues can be remedied. So, right, so as I mentioned, the Gaussian matrix model captures the effects of Euclidean wormholes and world line instantons, except for any contributions that involve crossing or intersecting, self-intersecting world lines or geodesics. So now I'm going to turn our attention toward finding a non-Gaussian matrix model that can reproduce disk correlators with any number of O insertions. So for now, we're only going to work on the disk and not include handles, not think about handles. So in general, we're looking for an interacting two-matrix model. And in general, such models are not solvable. So to make some progress, we're going to assume that such a model can exist, and we'll ask what properties it might have. So first, we're still going to consider a single trace matrix model potential. This is just for simplicity, and right now we have no strong reason to consider multi-trace matrix model potential. So again, we're looking for a theory of random matrices that can reproduce these disk correlators. So there's some trivial sense in which we already know of a theory that does this. Indeed, the SYK model is a theory of random matrices, in a certain regime of parameters. It's a theory of random matrices that will reproduce these disk correlators. But from the perspective that we're taking, the SYK model is an extremely fine-tuned model. And we imagine that there are probably many microscopic details of the SYK model that don't matter so much with respect to its ability to reproduce these correlators at low energies. In particular, we imagine that the SYK model might be a member of a universality class of many other models that have the same kind of symmetry breaking pattern at low energies. And so we kind of want to have some effective matrix model description of this entire universality class. And so the approach that we're going to take will be a bottom-up approach, where we write down a matrix model and we ask, what's the minimum amount of fine-tuning that we need to do in order to capture these correlators, or to, I guess, explain these results. Okay. So I'm going to show soon that this matrix model cannot be a conventional Tooft-scaled matrix model due to a certain constraint that's obeyed by the matrix elements of O. So first, just to be a little bit more precise about what I'm doing here. So I'm going to assume that we're actually working at a fixed typical instantiation of the H part of the matrix model, of the matrix integral. And so we can imagine that we were given some typical distribution of energies, and then we're just going to focus on the matrix model for the matrix O. Also, for simplicity, I'm going to rescale the matrix O into a matrix I'm going to call R, just by this function of energies, and this just makes the gravitational Feynman rule, where the bulk matter line intersects the ADS boundary, trivial. Okay, so here's the matrix integral for R. So again, it's basically the same as what we considered in the Gaussian model, except now I'm allowing a 4-point interaction between the R matrices. And again, F is a smooth function of energies, G is a smooth function of 4 energies. And so the point is that any correlator, is in general a product of Kronecker deltas times some function of the energies, which could also involve delta functions of these energies here. And any sums over internal loops and loop diagrams are basically sums over expressions involving these functions f and g. And so because f and g are smooth functions, these sums can be replaced with integrals using the density of states for h. And that's what I mean when I'm saying we're working at a typical instantiation of the matrix model, that to leading order in each of the S0, sums over eigenvalues can be replaced with an integral over the density of states. And that's what you get for every loop in a matrix model diagram. Okay, so as I've basically elaborated before, using the gravitational Feynman rules, we can infer what the connected correlators of R are. So for the 2-point function, it takes this form. And for the 4-point function, again, the connected correlator should be given by the 6J symbol over here. And then here are the Kronecker deltas, and summing over all the relevant permutations to get something that is symmetric on the left-hand side appropriately. And so just to drive this point home, I'm just going to go over some quick examples. So here, this gray blob here represents the sum over all connected planar diagrams that you can draw in the matrix model. So again, so the point I want to make is that, in our interpretation of this matrix model, the sum over all the connected 2-point diagrams should be equal to, the Feynman rule associated with the 2-point function. Likewise, the sum over all connected 4-point diagrams should be associated with the 6J symbol. And again, each of these loops here, which represents a sum over eigenvalues on the gravity side, is interpreted as an integral over the density of states. And here's just a more elaborate example, just to illustrate this point. So here, this blob over here represents, the sum of all the connected 6-point diagrams. And that's supposed to represent the sum of everything you would get from all these Witt contractions between these 6 external operators, such that all the Witt contraction diagrams are connected. So, all these blue lines are all connected to each other. Right. Meanwhile, we have this region over here, the sum over this loop. Well, this region over here corresponds to this region and doing the integral. And then here, again, we have a sum over 2-point diagrams, which again is just captured by this single Witt contraction line. So we really want to, dissect these gravity these diagrams, these gravity Feynman rule diagrams into, I guess, different components of a matrix model diagram in this way. This is kind of the interpretation that we're after. Okay, so now I'll finally talk about the constraint that the matrix elements have to obey. So first, let's consider the case where we turn off gravity and we just consider the generalized free field, where we can kind of see what the origin of these constraints are. And so for simplicity, let's work at 0 temperature, where the 2-point function is very simple, just 1 over the difference in Euclidean time to the 2 delta. And now let's consider some 2-point function where the dot 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 refers to other arbitrary operators. So to compute this, we have to sum over all the Witt contractions, and we can sum over the Feynman diagrams. Well, basically, we can put the Feynman diagrams that we'll sum over into 3 classes. The first class of Feynman diagrams will be diagrams where these 2 operators are contracted with each other. And then of the remaining diagrams, we can pair diagrams together where every diagram can be paired with a diagram that's the same diagram up to an exchange of the 2 legs that come into these 2 operators. So now, to see a constraint, we should compute the commutator of 2 operators that are separated in Lorentzian time. And the point is that the contribution from these 2 from these 2 diagrams, every diagram in its pair, will cancel out, basically because the commutator here is an anti-symmetric operation. And so we only have to think about the contribution from the diagrams where these 2 operators are paired with themselves. And so when you do that, you can compute the commutator and argue that the commutator in the GFF is proportional to the identity operator times some C number, which is given over here. So the point is that if we tried to model the GFF with some random matrix theory, we'd have to be really careful because general matrix elements sampled from a random matrix distribution certainly won't obey the fact that these 2 operators separated at Lorentzian times, they generally won't commute to give you the identity. But the point is, we're not going to focus on the GFF case anymore. This is just to motivate the presence of the constraint. So now I'll explain how this works in the matrix model side. So, right, so again, diagrammatically, for the GFF side, we saw that we had to think about, uncrossing or crossing 2 legs of a diagram in order to argue for the presence of a constraint. And so here, using the gravity Feynman rules, we know that the 6J symbol obeys this orthogonality relation, which earlier I gave an interpretation as uncrossing 2 lines. So I'll just repeat this figure over here from earlier. And now to explain the constraint, basically what I'm going to do is I'm going to take our matrix R, and I'm going to take, well, RAB times RBC, and I'm going to take the index B, and I'm going to average it over a microcanonical window. So that's what this red lettering represents. Basically, a red index means an index that's going to be averaged over a microcanonical window. So this red sum is a sum only over the microcanonical window, and I'm normalizing here by the number of eigenvalues in that microcanonical window. And I'm going to subtract the expectation value of RAB, RBC off of it, so that this thing on the left-hand side, which I'm calling N, will have 0 mean. Okay, so going forward, I'm going to omit this red summation and normalization, but that notation will always be implicit. So a red index means an index averaged over a microcanonical ensemble. And so here, this index is averaged over an ensemble, averaged over a microcanonical window at an energy that's specified by SB. And so now I've defined a matrix N, SB, and then the matrix elements of N are A and C, labeled by A and C. Okay. Okay, so now to get to what the constraint is, I'm going to consider this order 1 linear combination of matrices N for different microcanonical windows S. So here, the first term in this integral is actually, well, just N itself, because I have a delta function here. And so we're going to take that and subtract it from this matrix N, where I integrate the parameter S over all values weighted by a 6J symbol. And so that will define a new matrix, which I'll call M. So the point is that the Feynman rules imply that the leading planar contribution to a correlator with one M and any number of R's vanishes. And so I'll just illustrate this point here with 2 R's. So here is the graphical representation of a correlator with 1 N and 2 R's. And again, I'm averaging over a microcanonical window as appropriate, so that I can directly, make a comparison with the gravity computation, which only knows about microcanonical windows and nothing more fine-grained than that. So here, usually for a 4-point function, we would have 3 diagrams, but again, I subtracted off a contribution from N, which effectively kills one of the diagrams. And so the point is, now let's consider integrating over S1 with weighted by a 6J symbol. Basically what that does is, that has the effect of crossing 2 lines here. And so now that we've crossed the 2 lines, we can perform this integral over here of S1, and this will cause these 2 lines to uncross, as I argued earlier. And so the point is that the sum of these 2 diagrams is invariant under this uncrossing operation I just performed. And so now the point of this M matrix, which is like the constraint matrix, is that if I anti-symmetrize over this operation, then the contribution from these 2 diagrams cancels and we get 0. So basically, acting on N with this kind of integral kills fluctuations, or yeah, it gives you something that's suppressed. So I can be a little bit more precise about that. So let's take the matrix N, square it, and compute its expectation value. So just to compute the variance in the matrix ensemble, and it's going to be order e to the minus 3 S naught. And so we can estimate that the fluctuations of this matrix are at least of this order, roughly. Meanwhile, since we know the expressions for connected correlators to leading order in each of the S naught, then with a bit more work, it's possible to show that if I take an arbitrary correlator of these M matrices, with different values of the indices, that at most it's going to be order e to the minus 2n S naught. So it'll be more and more suppressed depending on how many matrices you've inserted. So this is a non-trivial step, but I just don't have the time to show that. It doesn't immediately follow from anything I've said. In particular here, I'm considering individual matrix elements of M that are not averaged over a microcanonical window. So this is a more non-trivial statement. But what follows from it is that we can compute the So we can take a matrix element, we can square it, and then compute its nth moments like this. And we can argue that they're going to be suppressed as e to the minus 4 n s naught. And since this holds for all the moments, it's reasonable to conclude that in the matrix ensemble, the fluctuations of the matrix M are order e to the minus 2 s naught. And so now here's the whole point. This is the whole point of the constraint. A generic order 1 linear combination of the matrix N, which is quadratic in R, should have fluctuations roughly at the order of e to the minus 3 halves s naught. But this matrix M represents a specific linear combination of these n matrices whose fluctuations are parametrically smaller, order e to the minus 2 s naught. So the point is that by taking an order 1 linear combination of an expression that's quadratic in the matrix elements, we can get something that is parametrically smaller. And so, if I were to take s naught to infinity, then this would exactly be a constraint. And so this is essentially the key reason. Well, okay, so I guess this is a key point that will guide our understanding of how this matrix model is supposed to actually work. Okay, so the big conjecture then is that we conjecture that the only reason why the Gaussian matrix model fails to reproduce the disk correlators is because the Gaussian matrix model fails to obey the constraint. So in other words, I guess we want to work towards some refinement of the ETH where basically the reason why it might not apply is because there's some certain constraints like locality that have to be obeyed in a certain theory. But once all that is taken care of and all the constraints are solved, then if there's no other special reason why matrix elements have to take some particular form or be constrained in a particular way, we might expect them to look as if they were generically sampled from some ensemble. And so here we believe we identified the relevant constraint in this example. So now how could this constraint actually be implemented in a matrix model? Well, the idea is to simply take this constraint matrix, square it, and then I guess take a trace and add this to the potential with a large coefficient. That should do the job. And now, the work we have to do that we're in the process of doing is to explicitly see this. So to be precise, we're interested in a 't Hooft scaled matrix model that is then double scaled. And in the double scaling limit, the quadratic and quartic terms in R, which would be produced by this term that we've added here, should become large in a way that enforces the constraint. So to check this, we actually need a proposal for what the correlation functions might look like before the double scaling limit is taken. These would be correlation functions that don't obey a constraint. And so we're going to take these correlation functions to be something I'm going to call q-deform Jt gravity. So I'm just going to go over this very quickly, but the idea is that q-deform Jt gravity is defined operationally from its Feynman rules, which are the same as the Feynman rules I've mentioned earlier, except all the special functions that appear in these Feynman rules can be deformed by a parameter q, which goes from 0 to 1. And the undeformed case I've been discussing until now is q equals 1. So the key difference between q-deform Jt gravity and Jt gravity is that in q-deform Jt gravity, the density of states is compact. It sits on a compact interval here, whereas in original Jt gravity, the density of states has an infinite range from 0 to infinity. This is just an expression for the q-deform density of states that just goes to the usual density of states as q goes to 1. Furthermore, the q-deform 6J symbol still obeys the Yang-Baxter equation, so it's consistent, but it does not obey the orthogonality relation. And so this implies that q-deform Jt gravity does not obey the aforementioned constraint. So now our conjecture is that the q-deform disk correlators can be captured by a 't Hooft scaled 2 matrix model.
Sorry, can I ask a question?
Sure.
Can you say a few words about the physics of this density of states? Why is it cutting off at some log of q? How are we supposed to think about this q-deform system?
That's a great question. The way I like to think about it is in the context of the double scaled SYK model that was studied in this paper by Berkuz and collaborators. So there, they wanted to compute the SYK model in a limit where the ratio of n divided by number of fermions in the interaction, which I'll call P. Sorry, it's n divided by P squared. That's supposed to be fixed as n goes to infinity. And
Sorry.
they show,
The number of fermion, like the Q of the SYK, the number of.
yeah, sorry. So people usually call the number of fermions in the interaction Q, but I've already used the letter Q for something else.
Right, but that's
Sorry.
a coefficient. Yeah, right. So you want the number of fermions. We usually take the number of fermions in the SYK Hamiltonian to be order 1 as n goes to
Yes.
infinity. But you want it to be square
Exactly.
root to n.
Exactly. So this is a scaling limit where the number of fermions in the interactions will scale up as n gets large. Mhm.
That model just basically scrambles instantaneously. There was a paper by Lenny Susskind just like a few days ago proposing that this is a dual of de Sitter. Do you know about this?
Yeah, I haven't had a chance to read that carefully yet, but when I saw that claim, yeah, I was extremely intrigued, and that's something I want to explore further.
But this model is like non-local at a level that is not even, it's way worse than SYK, right?
In terms of a bulk interpretation, yeah.
Like
I mean,
in terms of scrambling, how fastly it scrambles, way faster than log n. So it's faster than fast scrambler.
Right, because
So-
Q is, sorry, the number of fermions in the interaction is becoming very large. Yes.
Yeah.
Yes.
Yeah. Okay. Good. All right.
Yes. So, yeah, this will scramble very quickly. Yeah, that's a good point. Yeah, so this is something I'm kind of still actively thinking about, which is what kind of bulk interpretation might we want to give to this. But right now, we're kind of just viewing this as a means of defining a double scaling limit in a matrix integral. Okay, good. So here's the point. We're proposing that there exists a Tuft-scaled matrix integral that could capture these q-deformed gravity amplitudes, and that's conjecture is just based on the fact that these amplitudes don't obey a constraint. So perhaps this is possible. So now to test this conjecture I made earlier, our strategy is to write down Schwinger-Dyson equations for the two matrix model that's again presumed to be dual to Cubiform Jt Gravity. And in general, Schwinger-Dyson equations relate correlators and couplings. And so we're going to compute the correlators using the Q-deform Feynman rules. And then we're going to solve for the couplings, or try to solve for the couplings, or try to make some non-trivial statements about the couplings. And basically, by taking a limit that Q goes to 1, which is where this constraint is obeyed by the correlators, we want to check our conjecture. So in other words, can we explicitly see from these Schwinger-Dyson equations, can we make some argument that yes, in fact, the quadratic and quartic terms in this matrix model have to become large and scale in a certain way to enforce this constraint. So this is something we want to see explicitly at the level of the Schwinger-Dyson equations of the two matrix model.
Sorry, just one more question. So
Sure.
Q going to 1 is when the spectrum is basically like it's just 0, right?
When Q goes to 1, the spectrum is that of undeformed Jt gravity, which is just the cinch.
Oh, sorry. It was 1 over log Q. Sorry. Yes. Thank you.
Okay, good. Thanks. Okay, so here I've just reproduced the matrix integral that I'm talking about. It's really the same expression, but I've been a little more explicit about where n belongs because it's a Tuft-scaled matrix integral. Okay, so almost done. So these are the two Schwinger-Dyson equations that we're looking at here. Basically, so the first Schwinger-Dyson equation says, I can start off with this propagator in this diagram. Sorry, this yellow blob is a sum of anything that could be written in here, not just connected, but anything. So the point is that if I start with this propagator, it can either directly go to the other side, or it can go into a 4-point vertex. And then the remaining legs have to, contract with this last leg here in all possible ways. Or this leg can go into a 6-point vertex or an 8-point vertex, etc. That's what the ... means. And then we can consider a second Schwinger-Dyson equation, where again, we can start with this propagator, and it either has to contract into this leg, into this leg or that leg. Not this leg though, because that would be not planar. So then it could also contract into a 4-point coupling, and then the remaining legs have to get together in all possible ways. And then this could contract into a 6-point coupling, and so on and so forth. So the point of the Schwinger-Dyson equation is that the first equation can be used to solve for the propagator in terms of the higher point couplings. Okay, so the propagator appears here and here, but you can solve for it in terms of the higher point couplings. And then with the second Schwinger-Dyson equation, you can further solve for the 4-point coupling in terms of all the higher point couplings, and so on. But we're mostly interested in the 2-point and 4-point couplings of this matrix model. And then we're going to also assume that the higher point couplings are fine-tuned, so it's enough just to consider these two equations. So I guess I don't have time to go through all the manipulations of this equation here. But the point is, after many steps, or a few steps, we can take these two equations and combine them to get this equation here, which is an equation for the 4-point coupling in the matrix model. So let me be precise about what I mean here. Every diagram here is to be computed using the gravity Feynman rules, or I guess q-deform gravity Feynman rules. So every crossing of two lines of black lines is a 6J symbol. The only new thing I have to define for you is this new green vertex over here. And this is just a function of the 4 energies that meet at that vertex. And that function of the 4 energies is just given by the function g that appeared explicitly in the action for the matrix model. And again, g is a function of, it's a smooth function of 4 energies. It's a smooth function of 4 energies. So, so basically, okay, I guess I'm roughly out of time. So I'll just summarize what our main technical result here is. So basically all we want to do is solve this equation for the 4-point coupling and see if our conjecture is tested. So what we've been able to show is that if we ignore the ... dots, like if we assume that our model truncated at 4th order, then we can prove that this equation has no solutions. So this implies that higher order interactions are important. So now we want to go further and say, even if we're ignorant of the higher order interactions, we can still argue that the 4-point coupling might have to scale to infinity in the double scaling limit in a certain way to enforce the constraint that I mentioned earlier. So that's basically where we are. And so I guess I just have a quick summary slide here. So again, the goal of our work is to find a matrix model dual to Jt gravity with a free massive scalar that admits an interpretation in terms of the ETH. And as I've mentioned, the gravitational path integral implies that these matrix elements of O obey a constraint. And so we believe that this constraint should be enforced in the matrix model by a double scaling limit, where the quadratic and quartic terms become large in a particular way. And so to test this conjecture, we define the double scaling limit by introducing a q-deformation to the theory. And then we can explicitly study Schwinger-Dyson equations, which are well defined when q is less than 1. And then we can test to see if the couplings behave in the expected way as we take the double scaling limit. And if that's true, then that's evidence that such a model might actually exist. Okay, so I'll leave it there. Thanks very much for your attention and questions.
Thank you so much, David. Are there any questions? Actually, I'll start by asking a question about, I think this is a pretty like a rough question just regarding your first point. I kind of, I guess conceptually, I got confused about the fact that, so when you say it admits an ETH interpretation, you mean it's chaotic in the ETH sense? What I mean, I'm a little confused about the meaning of what does it mean to, yeah.
Oh, yeah. So what I mean is that, yeah, so basically I just mean that that there's an appropriate sense in which we can think of the matrix elements of the operator O as being sampled from some distribution. So they're random in some sense, but have statistical properties that can be described by the matrix model.
And then it would be key here that this matrix model, the coefficient of which has a macrocanonical suppression.
Yeah, that's right. So
But
That's
it is
impl-
ETH. It's like
Yeah,
full
the-
ETH.
the microcanonical suppression, that's implied by the matrix model. So the order of those fluctuations has to be just so in order to agree with the gravity correlation functions.
That's right. That's right.
Mhm.
Okay, thank you. Are
Yeah,
there any other
thanks.
questions? If not, let's thank David again.
Thanks very much. Mhm.
And we might bug you with some emails in the next coming days or weeks.
Yeah, that
Thanks
sounds
so much,
great.
David.
Yeah,
All right.
thanks for having me.
Thanks.